In this video, we're now going to be looking at geometric sequences. So a geometric sequence is an additional type of sequence where instead of it having a common value that you add or subtract every single time to go from the first term to the next, you're now going to multiply by a value. So here I have three different examples. Let's look at the first one. So if I have the first term is 2 and I go to 6 and then I go to 18 and then I go to 54, you can see that every single time I'm multiplying by 3. Now the name we denote when you have that value is the common ratio. So our little r is equal to 3 and we still use little a to represent the first term. So a is 2. Now, if I look at this next sequence over here, you can see that the numbers are getting smaller. Now, you might say, oh, what's happening is you're dividing by 2 every single time. So in that case, the common ratio is going to be a fraction. It's going to be a fraction of a half, which is the exact same thing as dividing by 2. Just want to keep it consistent. Okay. Now, if I have something like this, what does the common ratio look like? Now you can see that the common ratio, what's happening is we're timesing by 2, the number is doubling, but it's alternating, it's changing to be a negative, then a positive, then a negative. Okay, that makes a lot of sense that anytime you have a common ratio that's a negative, in this case, this one's -2, it's going to alternate because if you start off being positive and then you times by negative, that makes it a negative. But if now you times that negative by another negative, it makes it positive, and then negative, and then positive, and then negative. Okay, so these are just geometric sequences. The first formula we're going to unlock is the formula to define a geometric sequence. So we say that the sequence is a GP if the following is true. If the ratio between the second term and the first term is equal to the ratio between the third term and the second term, then we say that this is a GP. Okay, it is very similar to the way that we define whether we have an AP. So an AP is the difference between the first, second term and the third term and the second term. But in GP, it just makes a lot of sense for it to be division, doesn't it? Something you just have to keep in mind with this formula is that you're always putting the larger number on top. Okay, so let's go ahead. Example 1, is the following sequence a geometric progression? So for part A, I'm going to plug it into the T2 over T1 equals to T3 on T2 formula. So T2 is 512, T1 is negative 1024, this is negative 256, and this is 512. So if I put in my calculator, that's going to give me a negative half on this side, and this will also give me a negative half. So since the left is equal to the right, we can then conclude that this is indeed geometric progression. Okay, next, part B. Is this a GP? So if I plug it in, we're going to get, so T2 on T1 equals T3 on T2. Now you could put it in the calculator as 21 on 8 divided by 7 on 2, but sometimes there's like a little bit of a trouble with putting fractions in fractions, and honestly, sometimes it just takes too long to put in your calculator. So what I'm going to do instead is I'm going to write it with the division symbol. Yeah, what a throwback to Year 7 and A, right? So T2 is going to be 21 on 8, and then I'm going to write divide by the first term, which is 7 on 2. And then the same thing, I'm going to do 63 on 32, this is the third term, divided by the second term. Now, I usually always do this anytime I'm expected to do fractions and fractions. I just want to make sure that I'm putting in the number correctly into the calculator. All right, so there's going to be 3/4, and then 63 on 32 divided by 21 on 8. This is also going to be 3/4. So yay, this was successful. Left equals to right, so therefore this is a geometric progression. Lovely. Next, example 2, find the pronumeral in the following geometric sequence. So if I want to find the value of x, which is this unknown term here, so 7 is the first term, x minus 1 is the second term, and 63 is the third term. If they have told us that it is a GP, then you can actually use the above result. We know that it's true. We know that the ratio between the second term and the first term is equal to the ratio of the third term minus over the second term. So if we plug this in, we get x minus 1 over 7, and this is going to be equal to 63 on x minus 1. Now, another trick, if you don't know this already, this is a great thing to keep up your sleeve. Anytime you have a fraction equals to a fraction and you want to solve this equation, we have this rule called cross multiplying. So when you cross multiply, the thing that crosses multiplies together. So x minus 1 times x minus 1 is x minus 1 squared. 7 times 63 is 441. Okay, and then boom, no more fractions. You can solve this easily. So now if I want to solve for x, I'm going to square root both sides now. That gives us x minus 1 equals to the square root of 441 is plus or minus 21. Yes, I'm going to do the plus or minus. And then if I add 1, I'm going to add 1 to each value. So positive 21 plus 1 or negative 21 plus 1. I'm going to get x equals to 22 or negative 20. Okay, and you might be thinking, oh, why do I have a negative? That is possible. You could have a negative term here. Let's show that either of these options do make sense. So for the first option, we're going to get 7, and then we're going to plug in x equals to 22. So 22 minus 1 is 21, and there's going to be 63. You can see that in each term value, you're timesing it by a common value of 3. So what if I did the next one, which is negative 20? If I plug in negative 20 into here, negative 20 minus 1 is negative 21, and then 63. So in this case, the common ratio is going to be negative 3. You're timesing it by negative 3. Okay, perfect. All right, same thing, guys. So let's plug it into the T2 on T1 equals T3 on T2. Given that this one here is your first term, this whole thing here is your second term, and this whole thing here is your third term. So we get x plus 2 all over x minus 2 equals to 5x minus 2 all over x plus 2. And then once again, same trick, I'm going to do cross multiplication. The x plus 2's times each other to give us x plus 2 all squared. And then this becomes 5x minus 2 times x minus 2. Okay, so now I'm going to go ahead and I'm going to expand this. This one over here, when you expand a perfect square, recall that this is going to be a plus b all squared equals to a squared plus 2ab plus b squared. Please do not, under any circumstances, when you see this result, write it as x squared plus 2 squared. This is not true, okay? If you don't know what this expansion is, I would much rather you just break down x plus 2 all squared into x plus 2 times x plus 2 and then manually expand it and simplify it. I mean, best case scenario, I want you to remember that, but otherwise, this is also acceptable. This here, this will make teachers cry. All right, so that means this will be x squared plus 4x plus 4 is equal to, and if you expand this one out, rainbow method, we get 5x squared minus 10x minus 2x plus 4. Okay. Let's continue to simplify. We get x squared plus 4x plus 4 equals to 5x squared minus 12x plus 4. And I'm going to bring everything over to the right just to keep it positive. 5x squared minus x squared gives you 4x squared. Minus 12x minus 4x gives you minus 16x, and 4 minus 4 gives you 0. So it becomes quite nice. Now I'm going to factorize this to solve for x. Going to take out 4x, left with x minus 4. So therefore, our solutions here are going to be x equals to 0 and x equals to 4. Okay, so let's also test that this is true. This is also a really good habit to develop for when you do it in an exam. So if I sub in each of these values into the original sequence, we can see if they actually give us a geometric progression. So if I plug in 0, we're going to get, so this is when x equals to 0. Well, that's hard to see. Okay, this one here is when x equals to 0. So you're going to get 0 minus 2 is minus 2. That's positive 2, and that's minus 2. So very simple sequence over here. Goes from negative 2 to 2 to negative 2. And then you can imagine it keeps going to negative 2 to negative 2. The reason why is because what's our common ratio? It is negative 1. Negative 1 just changes the sign. All right, now what about if I substitute in 4? So if I plug in 4, 4 minus 2 is 2. 4 plus 2 is 6, and 5 times 4 is 20, 20 minus 2 is 18. Okay, so what's the common ratio here? Common ratio is indeed a 3. All right, perfect. Now that brings us to the next formula in this exercise, which is the nth term of a geometric sequence. So when you have a sequence, it is really, really important for you to first make the decision with yourself or the distinction with yourself and ask, is this an arithmetic or a geometric progression? The reason why it's so important to make that first like little thought or question with yourself is they have completely different formulas. If you just blindly choose whatever formula you want, you're not going to get the right answer. So over here we have the nth term formula of a GP, and it's given as Tn equals to AR to the power of n minus 1. So Tn is just the nth term, A is the first term, R is the common ratio, and n is the number of terms. So if I had a sequence and I wanted to find the 50th term in that sequence, this would be the formula that I would use. So let's start. Example 3, find the 6th and 15th term of the following sequence. So in this sequence here, I can see that our first term is 6, our common ratio is 3, and our job is to find T6 and T15. So first, if I want to find T6, we're going to use AR n minus 1. Oopsies, we're going to use Tn. And if I plug in to find the 6th term, I'm going to get T6 equals to A, which is 6, bracket 3 to the power of 6 minus 1. Okay, and that's going to give us 1,458. Now you might be quite suspicious at how large this value is, because if you look at our sequence, it's quite small, right? It's in the first or second digit. So how in the 6th term you're able to get this big number? That is the thing with geometric progressions. The numbers increase so exponentially fast because you keep timesing a number that is already so much larger than the previous number. Like if I were to list out 6, 18, 54, the next one is 54 times 3, which is 162, and you're like, whoa, that's already big. But if you times that by 3 again, it goes even bigger, and you're like, whoa, times it again, you get 1458, which is our 6th term, as proven. Okay, so now I need to find the 15th term, and you can imagine it's going to be very large. So T15 is going to be A bracket R to the power of n minus 1. This is going to be 28697,814. Massive. Lovely. Okay, moving on to the next question. Example 4. Find a formula for the nth term of the following sequence. So if the question asks for the nth term, it means that you're not looking for like a specific number. You're looking for a little equation or a little formula for Tn, which is going to be in terms of n. So n is going to be part of it. So in this case, we're going to let A equal to 2/3. Now, what does the common ratio look like? Now, I can see what it is, but if you can't, because fractions are a bit like, oh, help, it is just too much. What you can do is you always take the ratio between the second term and the first term. So T2 divided by T1. So in that case, if we get -4/9 divided by 2/3, this is going to give you -2/3. That is your ratio. So now let's go ahead and find the nth term. So the Tn is equal to A times R to the power of n minus 1. Okay, and that's it. That is your formula for the nth term. And honestly, you just leave it. If you wanted to combine it, because they have similar bases, but not exactly the same, because this base here is 2/3, but this base here is -2/3, what I could actually do is I could force this 2/3 over here to become a -2/3 by doing a little trick. And that little trick is that I'm going to times it by a negative, but I'm also going to balance it by also times it by negative. Because like -1 times -1 is just 1. Nothing wrong with timesing it by 1. So I could write it as -1 times -2/3, bracket -2/3 to the power of n minus 1. Do you see how this is just the same thing as that? I'm just like kind of like adding additional things to it. And what I'm going to do after that is I'm going to combine this term with this term, because now they have the same base. Now when you have two numbers with the same base timesing each other, you can combine them together and add the powers. So now this becomes 1 plus n minus 1, which is going to become n. So you get Tn equals to -2/3 to the power of n. And please do not bring this negative into there and make it a positive. It's not true. What this does is it's just going to alternate the negative sign, sometimes negative, sometimes positive. Okay, great. Next, example 5. How many terms are there in the sequence? So if I'm trying to find how many terms, I'm looking for n. We know that A is 2. The ratio, ooh, very large. R is 7. the way that you're finding like how many terms there are is kind of like you're letting the last term correspond to Tn. And then you want to figure out what number is this associated with. Like, is this associated with 10, like n is equal to 10? If that's the case, then there's 10 terms there. Or is it associated with n is equal to 13? Then that means there's 13 terms there. So I'm going to let Tn equal to 4,802. So if we go ahead and plug this into the Tn formula, you're going to get 4,802 equals to a bracket r to the power of n minus 1. And now our job is to solve for n. Now, I would always recommend to use logs. Sometimes teachers say to use trial and error. Don't really like that. Just use logs. Logs are the best. And they appear all the time in the exam, so you might as well get used to it. So let's divide this by 2, okay, to make n the subject. So just to recap, when you want to solve for a power, that's when you know to use logarithms. That is like the purpose of logs. If as I'm saying this, you're super confused, I really urge you to watch the log modules, the logarithm and exponential modules. They are super helpful and they just form such a good foundation in year 12 math. It is used in like basically across all topics. All right, so now I want to make the power the subject. So the way you make the power the subject is I'm going to bring the power down, and then this becomes log base 7 of 2,401. All right, and then now I'm going to add 1. We get log base 7 of 2,401 plus 1. If I put this in a calculator, remember that you write this as log of the big divided by log of the base. So you're basically in your calculator typing out log 2401 divided by log 7 plus 1. And this is going to give you n is equal to 5. Okay, now process that. You're like, 5, how's that 5? Remember, they just go up so quickly, right? If I find this middle term here, the ratio is 7. So 98 times 7 is 686. And if I times that by 7 again, we do indeed get 4,802. Perfection. All right, example 6. Which term of the sequence is this? Now, this is just worded differently, but it's the same process as the question we just did before. So we're trying to figure out if this term is in the sequence, which term is it? Is it the 5th term? Is it the 18th term? What number does it correspond to? So we're going to go ahead and we're going to let Tn equal to negative 81 over 128. Okay, so I want you guys to pause the video and have a go. We're going to let the first term, a, equal to negative 2. Ooh, ratio. The way we're going to do it is we're going to do the second term divided by the first term. So 1.5 divided by negative 2, that's going to be negative 3 on 4. So go ahead, pause the video and have a go yourself. So let's go ahead and go through this together. So we get Tn equals to ARn minus 1. We get negative 81 over 128 equals to negative 2. Multiplied by negative 3/4 to the power of n minus 1. Now, if I want to solve this, I'm going to get rid of the thing in front of the exponential. This here is your exponential. So we're dividing both sides by negative 2. That cancels. Negative 81 on 128 divided by negative 2 is going to give you 81 all over 256 equals to negative 3 on 4 to the power of n minus 1. Now, if I change this into a log, we're going to get n minus 1 equals to log base negative 3 on 4 of 81 on 256. However, as I'm writing that, I get like, a little bit icky because you can't take the log of a negative. So if that's the case, look, you can either drop the negative and it will give you the, like, it doesn't always give you the answer, but in these questions it will, or you could just do trial and error. So if I have these two here, I'm going to put random numbers here in this power until it equals to 81 on negative 256. So put in your calculator, negative 3 on 4, make sure it is in brackets. If it's not in brackets, not going to work. Okay, and then you want to keep plugging numbers into here until you get 81 on 256. So if I plug in to the power of 3, plugging into the power of 3 gives me negative 27 on 64, so that's not right. To the power of 4. Okay, so when putting in this to the power of 4, it does actually give you 81 on 256. So if in order for this to be a power of 4, then what does n have to be? Well, in order for this to be equal to 4, then n actually has to be 5, because it's like 5 minus 1 is 4. So that will be your answer. Now, even if you continued on with the log and you kind of ignore the negative, it would actually give you the answer. Okay, it's just, yeah. It's because of the fact that the ratio is negative. It's kind of messing up taking the log of a negative. Okay, question 7. Find the first value of n for which the terms of the sequence 1 on 25, 1/5, 1 exceed 10,000. Okay, so let's write down what we know. So A is 1 on 25. What's our common ratio? Well, I can see to go from 1 on 25 to 1 on 5, I'm actually timesing it by ratio of 5, which might seem a bit like, oh, how is that working? Because these are small. They're actually getting bigger. They're getting quite larger. All right, so ratio is 5, and then we're trying to figure out what is the first value of n, or n equals to what, such that the term in the sequence exceeds 10,000. So such that Tn is greater than 10,000. All right, so what we're going to do here is we're going to find an expression for the nth term of the GP. And then once you have that expression, we're going to let that be greater than 10,000 and then solve for n. So Tn equals Arn minus 1. We're going to get Tn equals to A times ratio to the power of n minus 1. And then now we're going to let Tn be greater than 10,000. Now Tn here is equal to this, so it's kind of like I'm subbing this into this inequality. So we end up with 1 on 25 times 5 to the power of n minus 1 is greater than 10,000. And then now if I want to solve this, I'm going to divide both sides by 1 on 25. This cancels. Divided by 1 on 25 is going to be 250,000. And this is going to be 5 to the power of n minus 1. Now, when you have an inequality, you could still use it to solve for logs. The only thing that you have to keep in mind is that if you have a base that is less than 1, then it's going to be a negative value, which means you flip the sign. But we won't worry about that too much right now. So if I change this into a log, we get n minus 1 is greater than log to the base of 5, 250,000. And then we get n is greater than this log value plus 1. Okay, so let's go ahead. If we get that, we get n is greater than 8.72 ... And then you follow this inequality sign, then n value that is greater than 8.72, because it has to be a whole number, is going to be the 9th term. So the 9th term is the sequence, is the first term that exceeds 10,000, which is like, what? How's that so small? But let's check it. So we have here, if I plug in into this formula, that our first term is 1 on 25, our ratio is 5, and then our 9th term is 9 minus 1. We're going to get, so this is just me testing it in, T9 is 15,625. And just to make sure that it's the first one, I'm going to plug in T8. So replace 9 with 8, you get 3,125, which means that this is indeed the first term. Perfect. All right, so it's very similar. I want you guys to pause the video and have a go at example 8. List out everything you know, and then plug it into the Tn formula. All right, so we're finding the first value of n for which the terms of the sequence, this sequence exceed this. So we're going to let a equal to 1. Our ratio is 0.9, and we're letting Tn be greater than 10 to the negative 6. So, we actually have to be a bit careful here with the inequality sign, because it says exceed, and when you hear the word exceed, usually you think, oh, it's bigger than that, it's more than that. But if you look at the values of the sequence, it's actually getting smaller and smaller and smaller. So we start off with the biggest number 1, but then it gets smaller and smaller than that and smaller than that. So in this context, exceeding actually means getting beyond 10 to the negative 6, which means getting smaller than 10 to the negative 6. So we're going to go ahead and let Tn be less than 10 to the negative 6. Okay, because in this case, exceed just means going beyond. All right, so I'm going to find an expression for Tn. So we get Tn equals Arn minus 1, or Tn equals to 1 times our ratio 0.9 to the power of n minus 1. Now if I go ahead and let our Tn be less than 10 to the negative 6, I'm going to plug this into our Tn over here. We get 0.9 to the power of n minus 1 is less than 10 to the negative 6. And if I go ahead and solve this, we're going to get, now this is where it is really important the way that you use inequalities and logs. So what I'm essentially doing every time I change the exponential into a log is I'm taking the log of both sides like this. Okay, because the opposite of an exponential is a log. When I do that, I'm essentially making this n minus 1 a power on the 0.9, because it's like log base 10, 0.9 of n minus 1. Now I can bring this n minus 1 to the front, and then we're timesing that by log of 0.9. Now, if I want to make n the subject, this log of 0.9 is just a number. So I can get rid of it and bring it over to the other side where this is also just a number. So if I divide both sides by log of 0.9, this is going to cancel, but you're going to notice that you might have gotten the impression that this is going to be a positive number because there's no negative whatsoever, but I want you to plug it into the calculator. Log of 0.9 is negative 0.045. Now, how do I know that it's going to be a negative? I can tell you, you can ask me, oh, log of 2.4, is that going to be positive or negative? I'm going to say it's going to be positive. How about log of 0.1? It's going to be negative. Log of anything less than 1 is going to be negative, always. Try it. If you go log of 0.5, negative. Log of 0.99999, even though it's really close to a 1, it is still going to be negative. Log of 0.00001, also a negative. So that means that when I divide by log of 0.9, it's going to have the same effect as dividing by a negative, which means we flip the inequality sign. So this means we get n minus 1 is greater than log 10 to the negative 6 divided by log of 0.9. And now if I pop that in the calculator, log of 10 to the negative 6 all over log to the 0.9, we get n minus 1 is greater than 131.126. And then if I add 1, I get 132.126 dot dot dot. And now if I follow this, n is going to be greater than this when n is equal to 133. So the 133rd term is when it exceeds 10 to the negative 6. Okay, now let's always test if this is true. If I plug this in to our Tn formula, I'm going to get 0.9 to the power of 133 minus 1. So T of 133 is going to be 9.12 times 10 to the power of negative 7. Okay, now if I test the one before it, 132, we get 1.02 times 10 to the power of negative 6. So this here, this is like this is essentially like right before this point. But I want to exceed it. I want to go smaller than that. So that means this is actually going to be the correct answer. Okay. The next example to fully master this topic, example 9, is in a geometric sequence, the third term is 18. So T3 equals to 18. The seventh term is 1458. Find the 12th term. Okay, now, and by now, hopefully you'd be able to recognize that this is going to be simultaneous equations. All right, so now if I plug them into the respective Tn formula, the Tn equals ARn minus 1, we're going to get the term itself is 18 for this one here. A and R are going to be our unknowns, and then our n value is 3. So we get 3 minus 1, or 18 equals to AR squared. And I'm going to go ahead and call that equation number 1. We'll do the same thing, plug this into our Tn formula. We're going to let the term itself be 1458. A and R are unknown. And this term corresponds to the seventh term. So that's n equals to 7. So we get 7 minus 1, and that's our second equation. Okay, now if I have these two as my simultaneous equations, if I want to solve for A or R, oh, actually, sorry, I need to simplify this. Okay, if I want to solve for A or R, usually you have to use like elimination method where you add or subtract and then eliminate it. But if I subtract these two from each other, AR squared minus AR6, it doesn't eliminate one of the variables. That's why it's called the elimination method. Is your goal is to eliminate it so it's only in terms of one variable, either A or R. So how are we going to do that then? And this is going to be one of the first times that when you have a simultaneous equation, you don't add or subtract the two, you're actually going to divide it. So if I do equation number 2 divided by equation number 1, let's rewrite it. So equation number 2 is this. And equation number 1 is 18 equals to AR squared. If I divide them by each other, notice how the A's cancel out. That's exactly what we want. We want it to go away, eliminate. And then R to the 6 divided by R squared. Well, index laws, if you have two numbers with the same base dividing, you subtract the powers. So that's R to the 4. And then 1458 divided by 18, that's going to be 81. So then now if you continue, the fourth root of this is going to be 3. Okay, beautiful. So now we have the value of R. We can very easily find A. So now I'm going to substitute R is equal to 3 into equation 1. We get 18 equals to A times 3 squared, or A is equal to 2. Okay. Now let's make sure we answer the question. It says find the 12th term. So if I want to find T12, it's going to be AR to the power of n minus 1, 2 times 3 to the power of 11 is going to be 354,294. Yay!